So, parallelism in other words is a fairly simple way of improving the throughput, which applies in the case of these kind of especially the FIR filter type of structure, right. There is one additional twist to this that I will just mention before we move on to another approach that can be used to improve throughput, which is slightly more interesting in general. The twist that we can observe as far as parallelism is concerned is, if you go back and look at this diagram over here, you will notice that, for example, this x of n minus 1 is occurring in two places. Similarly, x of n minus 2 is occurring in two places, right, and I am effectively having to put two registers over there and generate those data, right, separately. What if I try and sort of combine that? What it would look like is something like this. Okay. So, what this means is, I have now separated out the x of n which was coming in over here, I will call it x of k over here, and basically say that I can split it up into two streams. Okay. The even numbered values of x go up, the odd numbered values of x go down. Okay. And the clock that is given to the corresponding registers has a time period of 2t rather than t. Okay. And what that means is, what are the outputs of these registers going to look like? If x of 2n is being fed to the top register, what was it that appeared one clock cycle earlier at the output at the input of it, and therefore is currently going to appear at the output of that register? X of 2 into n minus 1, or x of 2n minus 2. Okay. So, what you are going to see over here is x of 2n minus 2, not 2n minus 1, because only even numbered values are going here. Okay. So, the way to think about it is, x0, x2, x4, x6 are the values that are going in here, and x1, x3, x5, x7 odd numbered values are going to the bottom stream. So, if x0 is appearing at one place, or rather x2 is appearing at one place, the previous value that came there was x0, and that is the one that is going to be the output of this. x1, in other words, never makes an appearance on the top at all. Similarly, x0 or x2 never make an appearance on the bottom stream at all. And with this, what we can do is, now I just have these two registers, okay, and I can write down two new equations which basically say y of 2n equals a times x of 2n plus b x of 2n minus 1 plus c x of 2n minus 2, and y of 2n minus 1 equals a x of 2n minus 1 plus b x of 2n minus 2 plus c x of 2n minus 3. Okay. Now, how do I get these values? All that I need to do is observe that if the input on the lower register was x of 2n minus 1, its output is x of 2n minus 3. Therefore, I have all the values that I need. Multiply this by a, this by b, this by c, okay, and add them up. I am just drawing one adder over here for simplicity. In reality, you will need a chain of two adders, and this basically generates y of 2n, okay. And similarly, take this one, this one, this one, y of 2n minus 1. So, what has happened? The amount of hardware that I use in terms of the number of multipliers and number of adders remains the same. Nothing has changed over there. Okay. But if you observe this a little carefully, what you will see is that everything from this point onwards, from the point that you have made this split, right, everything to the left of it has a clock period of t, and everything to the right of it has a clock period of 2t. Okay, the registers are basically operating with a clock period of 2 times t. Okay. Why is this important? Because if you actually try doing a timing analysis on the right hand side of this circuit that I have shown over here, what it means is that all your static timing analysis, your critical path computations and so on are now trying to meet a timing goal of 2t rather than t. It is much more relaxed, it is easier for it to meet that timing constraint. Okay. You can use, if necessary, you can even use slower multipliers and adders. Okay. And by using that, whatever is on the right hand side finally will come down to operating at a slower speed. Now, how do I fix this? What I need is at the opposite end, once I have done all of this computation, I need to take these two streams and combine them back into a single output, right, which will basically give me y of n. And what that means is that over here, once again the t clock is equal to t. On the left hand side over here, t clock was equal to 2t. Okay. So, this entire area in the middle, in other words, right, is operating at half the frequency of the actual input. Now, this is potentially a very good thing, because one thing in general, if you need to operate something at a lower frequency, it is easier to do. Why? Because you do not need to worry too much about optimizing your hardware to a very great extent, right. You might be able to get by with smaller transistors with lower drive strengths that are still able to meet the longer clock period requirement that you have. Okay. And the other thing that you can do potentially is, this is one part where you need some familiarity with digital IC design. What is the connection between the operating voltage and the propagation delay through a circuit? In general, if I increase the operating voltage, keeping the technology otherwise the same, would I expect to see an increase or decrease in propagation delay? I should see a decrease, right. In other words, the circuit can switch faster, right. So, in other words, for a given technology, right, let us say it is a 45 nanometer technology, if I operate my transistors, if the supply voltage that I give is increased, it means that the transistors can now deliver a larger amount of current, they can charge the output transistors, output capacitors faster, and therefore the propagation delay will decrease. Conversely, if I reduce the supply voltage, I will end up increasing the propagation delay. Okay. Now, as far as this particular structure is concerned, what it tells me is I am allowed to increase the propagation delay, which means that I may be able to get away by operating at a lower clock frequency.